Welcome everyone. Today, we'll explore the fundamentals of material structures. Understanding atomic and molecular arrangements is key to predicting material properties and performance. This knowledge forms the foundation for engineering applications across industries. We begin with atomic bonding and solid-state structures. These concepts explain why materials behave differently under mechanical, thermal, and electrical conditions. Atomic bonding is the fundamental force that holds atoms together in materials and dictates their properties. There are three primary types of atomic bonds: ionic, covalent, and metallic. Ionic bonding occurs when electrons are transferred between atoms, typically between metals and nonmetals, resulting in strong electrostatic forces that make ceramics hard and brittle. Covalent bonding involves the sharing of electron pairs between atoms, creating directional bonds that are extremely strong, as seen in materials like diamond and silicon. Metallic bonding is characterized by a sea of electrons that are free to move throughout the lattice, which imparts ductility and electrical conductivity to metals. The strength and nature of these bonds influence melting points, stiffness, thermal expansion, and electrical properties. For example, materials with strong covalent bonds often exhibit high hardness and low thermal expansion, while metallic bonds allow for plastic deformation and excellent electrical conductivity. Understanding these bonding mechanisms is crucial because they form the basis for interpreting why materials behave differently under mechanical, thermal, and electrical conditions. Solid-state structure refers to the arrangement of atoms in a solid material. Crystalline solids exhibit a repeating lattice structure with long-range order, where atoms are organized into unit cells that repeat throughout the material. This regularity gives rise to predictable properties such as anisotropy in single crystals. Most engineering metals are polycrystalline, meaning they consist of numerous grains separated by grain boundaries, which significantly influence mechanical strength, corrosion resistance, and diffusion rates. In contrast, amorphous solids, like glass, lack long-range order, resulting in different optical and mechanical behaviors compared to crystalline materials. Grain size and orientation within polycrystalline materials affect properties such as toughness and fatigue resistance. For instance, fine-grained metals generally have higher strength due to grain boundary strengthening, while coarse grains may improve creep resistance at high temperatures. Understanding solid-state structures is essential for predicting material performance and tailoring properties through processes like heat treatment and alloying. Next, we'll look at metallic crystal structures and how metals solidify. These factors determine mechanical properties and performance in service. Metals crystallize into specific lattice structures that determine their mechanical properties. The three primary metallic crystal structures are face-centered cubic or FCC, body-centered cubic or BCC, and hexagonal close-packed or HCP. FCC structures, found in metals like aluminum, copper, and nickel, have multiple slip systems, making them highly ductile and suitable for forming operations. BCC structures, such as ferritic iron at room temperature, have fewer close-packed planes, resulting in higher strength but lower ductility, especially at low temperatures. HCP structures, seen in magnesium and titanium, exhibit limited slip systems, leading to anisotropic properties and reduced ductility compared to FCC metals. These structural differences influence how metals respond to stress, temperature changes, and deformation processes. For example, FCC metals are preferred for applications requiring high formability, while BCC metals are used where strength and hardness are critical. Understanding these structures helps engineers select appropriate materials for specific applications and predict their behavior under service conditions. Solidification is the process by which a liquid metal transforms into a solid, and it plays a critical role in determining the microstructure and properties of the final material. During solidification, nucleation and growth occur, forming grains whose size and morphology depend on cooling rates and alloy composition. Faster cooling generally results in finer grains, which enhance strength due to grain boundary strengthening, while slower cooling produces coarser grains that may improve creep resistance. The release of latent heat during phase change creates a plateau in cooling curves, which is important for controlling solidification in casting processes. Segregation of alloying elements and dendritic growth can lead to non-uniform properties and defects in cast components. Understanding solidification mechanisms allows engineers to optimize casting and welding processes, minimize defects, and achieve desired mechanical properties through controlled cooling and post-solidification treatments. Now, let's discuss crystal defects and how they impact mechanical behavior. Defects are not always bad, they can be engineered to improve properties. Crystal defects are imperfections in the atomic arrangement of a material and are classified into point, line, planar, and volume defects. Point defects include vacancies, interstitials, and substitutional atoms, which can alter diffusion rates and electrical properties. Line defects, primarily dislocations, are critical for plastic deformation as they enable slip in metals. Planar defects such as grain boundaries and twin boundaries influence strength, toughness, and corrosion resistance. Volume defects, including voids and precipitates, can act as stress concentrators and initiate failure under load. While defects may seem undesirable, they are essential for tailoring material properties. For example, controlling dislocation density through work hardening increases strength, and introducing precipitates via heat treatment enhances hardness. Understanding defects is vital for interpreting failure mechanisms and designing materials with optimal performance. Elastic deformation occurs when a material returns to its original shape after the removal of stress, following Hooke's law where stress is proportional to strain. Plastic deformation begins at the yield point, where permanent changes occur due to dislocation movement. Work hardening during plastic deformation increases strength by creating obstacles to dislocation motion. The stress-strain curve illustrates these behaviors, showing elastic limits, yield strength, and strain hardening regions. True stress-strain analysis becomes important near fracture, especially during necking. Understanding these concepts is crucial for predicting material performance under load, designing components to avoid failure, and selecting appropriate forming processes. For instance, metals with high ductility can undergo significant plastic deformation before fracture, making them suitable for shaping operations, while brittle materials fail with little plasticity. Finally, we'll cover fatigue, diffusion, and property modification techniques that enhance material performance. Fatigue crack initiation occurs under cyclic loading, typically at stress concentrators such as surface defects, notches, or inclusions. Over time, cracks propagate with each load cycle, and fractographic features like beach marks and striations reveal the failure history. The SN curve describes the relationship between stress amplitude and cycles to failure, highlighting endurance limits for certain alloys. Environmental factors and mean stress significantly affect fatigue life. Diffusion, the movement of atoms within solids, is governed by Fick's laws and is highly temperature dependent, following Arrhenius behavior. Diffusion processes are critical in applications like carboizing for surface hardening, hydrogen embrittlement prevention, and oxidation resistance. Both fatigue and diffusion influence material selection, design, and maintenance strategies, making their understanding essential for ensuring component reliability and longevity. Property modification techniques allow engineers to tailor material performance for specific applications. Grain refinement increases strength through the Hall-Petch relationship, while solid solution and precipitation hardening enhance hardness and wear resistance. Heat treatments such as quenching and tempering balance strength and toughness in steels, and annealing restores ductility after cold work. Beyond metals, ceramics exhibit ionic or covalent bonding, high hardness, and brittleness, with strength controlled by flaw size and porosity. Polymers consist of long-chain molecules with structures ranging from linear to cross-linked, influencing properties like flexibility and thermal behavior. Composites combine a matrix with reinforcements such as fibers or particles to achieve superior strength-to-weight ratios and tailored anisotropy. Understanding these material classes and modification methods is crucial for selecting the right material and processing route to meet design requirements.